right, good day. Welcome to lesson 7.2. All right, so you started chapter 7 2 days ago, and we started with transformations. What chapter 7, the remainder of it's going to be about, is your second major function, which is an exponential function, right here across the top. And we actually have three main functions in Algebra 1 we have to focus on. So let's see if we're in pen mode, and we're not, so turn that on. All right, so the first function we've learned about so far is linear. Quick review here. Okay, the parent of all linear functions is y is equal to x. And there's only one thing that you know that are on this that will tell me it's linear. It's because the highest exponent of the x term is a 1. And if I took this to slope-intercept form, it would be y is equal to a slope of 1, x plus, and it would have a y-intercept that is the origin, 0, 0. So that's linear. Okay, we're going to take on exponential for this chapter. In chapter 8, we do quadratic. And those are the three main ones. That's going to be the bulk of the state test. So let's put a quadratic up here just for comparison. You've seen quadratics before. And the parent for all quadratics is y is equal to x squared. And I brought this up so you could see. X to the first power, x squared. We have a cubic function that is y to the third, y is equal to x to the third power. But we're going to focus on exponential functions, and so what we're going to have is the x value, or the input, is actually going to be an exponent in the function. So let's get rid of this. And let's go back and review just a little bit. Okay, exponents are instructions for repeated multiplication. So an exponent says, multiply this to itself this many times. Then we did negative exponents. I think it was chapter 3. Negative exponents say, find the reciprocal and remove the negative. So we're going to be doing that today. Let's review it a little bit. So 2 raised to the 4th power says, go multiply 2 to itself 4 times. 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16. And of course you have a calculator, so you don't necessarily have to do that in your head. All right, so I've got 2 to the negative 4th. Okay, well, the reciprocal of that would be 1 over 2 to the 4th power. Okay, that's the reciprocal. And that's going to give me, and I know 2 to the 4th is 16. That's going to give me 1/16. Okay, now I've got it the other way around. 1 over 2 to the negative 4th. Okay, I'm still going to do the reciprocal. So flip that around, remove the negative, and I have 2 to the 4th over 1 is equal to 16. So several different ways you can look at that, and we're going to use all of them today. Since we are starting a new function, we've got vocabulary. I've got an exponential function, and I've got it in 2 different forms. And these, it's unlike linear, there's not 2 different ways to know this equation. When we get to quadratics, you're actually going to have 3 ways, including the parent. All right, exponential function, a function in which the input x is an exponent. So there's the input, which is the exponent. There's the input, which is the exponent. The parent is f of x is equal to b to the x, which is interesting because I've got a b right here, which means I can't change this to a y and put this in my calculator to graph it because I can't graph it unless I have a number that's a value for b. We're going to be dealing mostly with standard form. So what's the difference? I've got this a right here. We're going to diagram this in great detail on the next page, but right now, pretty much every function we're going to deal with in standard form has got a y-intercept. So we'll lay that out in a minute. All right, the value of b has a name, and it's got several different names, but primarily we call it the multiplier. So the value of b has restrictions. It says that b must be greater than 0 and that b cannot be equal to 1. And we're going to explore that in a minute too. The multiplier is known as a growth factor when b is greater than 1. It is known as a decay factor when it is a fraction or a decimal that is between 0 and 1. So a decay factor would be something like 1/3 because that's less than 1. Or let's say 0.75, which is also, oh, that got a tail on it. Let's get rid of that. I meant to say 7.5, which also happens to be 3/4. Those are a fraction and a decimal that would fall between 0 and 1. And then we have another way to look at this. And we're going to, when we get into word problems, we're really going to delve into this. And I'll repeat this box again when we get into the word problems. So what I have here is a rate. Now this is going to be a rate of change for this function, but it's really important that you note this. This is not a constant rate of change. It varies, which means that I'm going to be working with a fraction or percentage, but fractions and percentages aren't constant. Every time I move forward by 1 in x, the amount of the fraction or the amount of the percentage is going to change. And we usually write the fraction or the percentage as a decimal, and I have a growth rate and a decay rate, just like I had up here. Same thing, my growth rate is going to be greater than 1. My decay rate is going to be a fraction or a decimal between 0 and 1. And this is how I find the growth rate. I turn the fraction or percentage into a decimal, and it's 1 plus whatever that decimal is. That's going to result in the total amount with the increase. And Ms. Hinson says I should have put plus here instead of with, so we'll go ahead and put plus here. I can take criticism. Okay? And then I have a decay rate. Again, this is going to be a decimal. That is going to be, because it's decay, between 0 and 1. And the way I convert that into a multiplier is it's 1 minus that decimal. And that's going to result in the total amount less the decrease. Don't get weirded out. We're going to get this later on. We get the word problems. I'm going to repeat all of this and it will all make sense. Okay, this word we are going to use today a lot. And we're going to look at the graph of exponential functions. This word is asymptote. And an asymptote is an invisible line. It's not part of the graph. It's an invisible line that the graph is going to approach, but it is never going to cross. And asymptotes are written as equations of lines. In this case, we're going to write equations of horizontal lines. So they're going to be y is equal to some number because they're horizontal lines. Get rid of this. All right, we're going to look at a growth graph and a decay graph. These are properties of exponential functions. And I'm going to see if I can get this to fit on the screen. Let's see if we can move this up a little bit. Nope, that didn't help. So we're going to put it back down. All right, look at the graph first, then we're going to fill in the table that goes with the graph. They match. So I've got, this is a graph for exponential growth. Okay, number one, it is exponential growth. This graph is increasing from left to right. It is increasing. And how does it increase? It increases very slowly. Then it hits some point of critical mass, and it just shoots to the sky. And of the three functions that we're going to learn, nothing increases more rapidly than exponential growth. Okay, we have growth when our value for b in our equation, y is equal to ab to the x, is greater than 1. And this particular graph, I've got f of x is equal to 2 to the x power. So my b value is greater than 1, it's a 2. All right, here's the famous asymptote. It's this invisible line right along here. And this graph right here, down here, it is approaching 0. But it never, ever, ever is going to reach 0. It just gets smaller and smaller and smaller, but it never actually becomes 0. And so this asymptote has an equation right here. It is a horizontal line that just happens to be the y-axis. You're going to see that changes in a minute. And the equation for the x-axis is y is equal to 0 because that's what y is right here. Y is 0. That's where y is equal to 0. All right, now compared to that, this is a graph that is exponential decay. And this graph is not increasing, this graph is decreasing. That's what decay sounds like. This is f of x is equal to 1/2 to the x. 1/2 is a value for b that is between 0 and 1. And what's happening here? It decelerates very, very quickly. It just drops like a rock, and then all of a sudden it tapers off, and it moves down here, it moves down here. It gets incredibly close to 0, but it never actually reaches 0, which is what the phenomenon is that is the asymptote. So the invisible line here is the same. It is right here on the x-axis, and that's where y is equal to 0 right here. So it's an invisible line that happens to be the x-axis. That's going to change later. You're going to see why it can. And the equation for the asymptote is y is equal to 0. Okay, so let's look at a few values in this table that made up this graph. And let's look at a couple of key points before I start erasing and scrolling. Right now I've got a y-intercept that's right here. And if I look down here, it's the same equation. It's y is equal to 2 to the x, and I gave you some numbers. So we've got a -3 as an input, a -2, a -1, a 0, 1, and down here a little further I've got 2 and 3. So if I replace that x with a -3, then I get the reciprocal of that, which is 1 over 2 to the 3rd power. 2 to the 3rd power is 2 times 2 times 2. 2 times 2 is 4. 2 times 4 is 8. So this happens to be 1/8. And if I look down here, that's going to occur about right there. A -3 and a 1/8. Okay, now I put it in -2. Again, it's a reciprocal. So 1 over 2 squared, which is going to give me a 1/4. And if I look over here, that's about where I am. My y value is between 0 and 1 and about 1/4. Okay, at a -1, I've got 1 over 2 to the 1st power. Anything raised to the 1st power is itself. So I have a -1 and a 1/2. Anything raised to the 0 power is 1. So there's the y-intercept, 0, 1, which is right there. Then I've got 1 and 2 to the 1st power, which is 2. And that is right there. And if I keep going down here, I've got I've got a 2 and a 3, and that's going to give me, and I should really actually go down there. I hate to do that to lose this though, but I guess we will. Okay, here's the rest of the table, and we'll compare it when we get back up there. All right, so I'm putting in a 2. That's going to give me a 4. And we've erased everything else, but that 2 to the 4th is right, or 2 and 4 is right there. Here's 2 cubed. That's going to give me an 8. And that's off the screen now, but if you printed this, you know that it's up here, about right here. So I've got some really good grid points. I've got a y-intercept, and then I've got stuff that's tapering off here that is never ever going to reach 0. Okay, let's look at this one. Let's go back up to this graph. We can get most of this one on. All right. Here comes the lunch announcement. Brace for it.
Second lunch. Eat in. Second lunch.
All right, this one is the decay one. This has the b value that is between 0 and 1. So when I get down here at the table, I have 1/2 to the x or 0.5 to the x. I don't care which one you use. So I'm going to put the input of a -3 right there. That tells me I'm going to take the reciprocal, and that would leave me with a 1 like that. I don't need it. So 2 to the 3rd power, 2 times 2 is 4, times 2 again is going to give me an 8. Starting to look familiar? Okay, so there's the 8 right there. That's a really good grid point. And now I've got a -2. Again, I've got a reciprocal, so I flip that over, lose the negative. 2 squared is 4. And let's see, that's right there. And here's my -1 is going to give me just 2 to the 1st power, which is a self. So that's there. And here is the y-intercept. Anything raised to the 0 power is 1. So I have exactly the same y-intercept I had for the other one, right here. And then this is going to taper off. And if you remember, these are positive exponents, so that's just going to be 1/2. This one's going to be 1/4. And there is a 3 below this, but I'm going to put it right here instead of moving down. And so that would give me 1/2. I'm replacing this. I started with a 3. Here's what's in the middle. That's going to give me 1/8. So you can see that the tables are actually reverse images of each other. So I've got a point here, I've got a point here, and a point here, just like I did on the other one. This one is increasing, this is growth, this one is decreasing, it's decay. They are mirror images. I didn't have any kind of strange transformation. The difference is in what's happening with B. If the value of B is greater than 1, my graph is going to increase like this. Regardless of where the y-intercept is or anything else, the graph from left to right is going to increase. But if my B is between 0 and 1, which in this case it's a 1/2, this graph is going to decrease. Y-intercept might move, other things might change, but it's always from left to right going to decrease. That's the big point from here. Okay, let's clear this. Let's take a look at this equation. That's what's at the top of the next page. All right, there is a parent form, and we've looked at that. It was just y to the x, or y is equal to b to the x power. This is the one we're going to use more than any other one. This is standard form. Okay, it's a function, so it's got things in common with linear functions, and quadratic functions are going to have the same thing. I've got an f of x here that is the same thing as y. This is the output, it's the dependent variable, and it's the range. Now again, this is an exponential function because the x, which is the input, is the exponent. So that's the input, it's independent, it's a domain. So what can I say at this point? I can say that for all functions, the two things they will always have in common is they will all have an input that means exactly the same thing every time, and they will all have an output that also means exactly the same thing every time. What's going to vary is everything else. Always an input, always an output, and here's the rest of it. All right, most functions, most forms are going to have one form or another that's going to show the y-intercept. And you're going to see that when we get to the quadratics. So this a value is going to give me the y-intercept. It's going to be at 0, whatever the value of a is. And we get to the word problems. This is the initial value, just the same way it was when we had linear functions. All right, B. B is going to be in general called the multiplier. It is sometimes a growth factor. It is sometimes a decay factor. It is growth if it is greater than 1. It's decay if it's between 0 and 1. There's something unusual here we haven't seen before. We have constraints on B. We've used the word constraint before. It means I have a limitation or a restriction. So this is saying, guess what? There are things that B cannot be. It won't work if it won't. So I've got B is greater than 0. This actually means two things. B is greater than 0 says that B can't be negative. B must be positive. That's a terrible U, sorry. Greater than 0 says it's got to be positive. Okay, greater than 0 says that B cannot be exactly 0. And this one's straightforward. It says B cannot be 1. And later on in the practice, you're going to do a little bit of an exercise to explore and see what happens if B happens to be negative, or if B is 0, if B is 1. You're going to see why you've got this. Oh, I wrote constriction instead of constraint. How unpleasant. So let's write constraint. That's what it's what you get when you try and spell and talk at the same time. Constraint. Much better. All right, so speaking of practice, I've got a couple examples to go through before you get into the practice. So let's go ahead and erase this and scroll. All right, we've got the equation here. It is in standard form. And we've got a really strange looking graph that I'm going to explain to you in a minute. Okay, the first set of exercises are going to ask you to do this. For each exponential equation, determine if it is growth or decay, find the multiplier and the y-intercept. Okay, so remember, these are going to be in the form y is equal to a b to the x. So we always put parentheses around this. Some people will let you put a dot here for multiplication, but I don't. All right, so taking this apart, this is the y-intercept from left to right. That's the y-intercept. So I'm going to put, with better handwriting than that, a y-intercept. And we're going to write them like y-intercepts. We don't put 3's. We put 0, 3's in parentheses. That's after we get the pen activated. That's what a y-intercept looks like. And it's important that you know that the y-intercepts start with 0. All right, then I have a multiplier that is 5/8. Okay, well, what did we say about multipliers? We said that it is growth if b is greater than 1. Okay, well, that b is not greater than 1. 5/8 is going to be between 0 and 1. It is decay if it is between 0 and 1. So this is decay. I set this up so you could circle it, but I wrote that 5/8 really big. All right, next one. I've got a -2. Now, b can never be negative, but the y-intercept obviously can be. So I've got a y-intercept right here of 0, -2. And here's my b value. It's 7/2. Now, don't be misled. All fractions are not between 0 and 1. 7/2 is actually, 3.5? So that's greater than 1. So 7/2 is actually going to be growth. So that's what you're doing for the first part. All right, for the second part of the practice, actually I think it's like the third part of the practice, we're going to explore this transformations with these, mostly so you can see what happens with this asymptote and you can get the idea of an asymptote fixed in your head. So I've got two graphs here. I've got f of x and g of x, and it says the graph of g of x is the graph of f of x transformed. So it's in a dashed gray line so that you can see this is where it started and this is where it is now after the transformation. So describe the transformations, then write the equation of the asymptote. All right, now we don't necessarily have three transformations, but three transformations are possible, so that's why you've got three lines for this. So how are we going to do this? Well, first of all, this has definitely gone down, and it went down by 1. So there's no doubt about it. We have had a vertical shift. We're going to use the shorthand you learned in the last lesson. Down 1. All right, now we're going to look and we're going to see if we had either a stretch or a compression. And sometimes that's really hard to tell. And you usually don't get this nice gray shadow of a graph. That's just shadow of the graph. So I put this here to help you out. Let's see what happened here. Here's where this graph curved, pretty much right here at the y-intercept. And if y had a stretch or compress, then this graph would no longer go up 1 and over 1. So let's go down here and see if we can find where that curve is. And it's about right there. And it still looks to me like we are still going up 1 and over 1 right there. So it didn't stretch because this would have moved and it would have been like up 1 over 3 or up 1 over 2 or up 1 over 4. It didn't compress, or it would have been up 1 over maybe 2 or 3 or 4 this way. So we don't have a stretch or a compression. But we started out here, so not only did we move down, we also moved to the left. So we've had a horizontal shift. Let's see if we can figure out where that was. All right, now remember this graph actually went down 1. And I'm going to get rid of some of these lines so you can see what's going on. So we need to figure out how far left it went. And you might be really tempted to say that it went over 2. But I think it went over farther than that, because remember this graph went down as well. So we're going to take this same point, this place where it made the curve and where the y-intercept started. So that is a reference point. A reference point means it's someplace something I can use to make comparisons. So I've used the reference point when we talked about stretching and compressing. I'm going to use this reference point to make sure that I understand where my horizontal shift has been. And it doesn't necessarily have to be the y-intercept. It might be another point you find on the graph, but it's something that's really useful. Okay. So going from there, we know we went down 1. So look how far we actually went left. 1, 2, 3. We didn't go 2. We went 3. So I have a horizontal shift, and it went left 3. Okay, the last thing I have on here is I need to find the equation of the asymptote. Remember, the asymptote is not actually part of the graph. It's an invisible line that is right here. It's actually going to run up a little higher than that. And this graph is going to approach this invisible line, but it is never, ever going to cross it. And in this case, it's a horizontal line. And horizontal lines have equations that start with y. So what's the y value right here? It's -1. So this horizontal line has an equation that is y is equal to -1, and that's what my asymptote is. All right, that takes care of all the examples, but let's go look through the practice so you can see what you have to do today just quickly because this is a really short lesson. And I want you to be prepared. So I'm going to erase all of this. And let's scroll down to the practice. Okay, so just like we talked about, here's the ones where you're going to find the y-intercept, you're going to find the multiplier and determine if it's growth or decay. And here's the ones where we just did that you're going to describe the transformations and write the equation of the asymptote. Here's the three that I talked about where you're going to explore this idea of the constraint on b. B has to be greater than 0. That means B has to be positive and it can't be equal to 0. So we're going to give B a negative value and see what happens. Then we're going to make B 0 and see what happens. And the last constraint was that B cannot be equal to 1. So we're going to make B equal to 1 and see what happens. And then there is a small graph here. And your function you're going to explore is y is equal to 3 to the x. And you should have a problem with that. All right, so this is a one-day lesson. Shouldn't be too complicated. Enjoy. Thanks.